Okay, now let's look at single target tracking techniques. And the first single target tracking techniques we're going to look at are angle tracking techniques. And you can see there are a lot of different ways that we do angle tracking. And so this is actually going to boil over into the next lecture, the next section of this lecture, which will take us on and on. But we're going to be talking about mostly in this this section from view graph 17 on, we're going to be talking about amplitude monopulse techniques. And here are two radars that use amplitude monopulse techniques. If you looked out very closely, you'd see there are 4 feeds at the end of this FPS 16, and if you looked in here, you'd see similar type feeds. Now, in single target tracking techniques, I wanted to give you a feeling early on overall about the tracking process. Just in words, and not going into a lot of detail. And just what the functions of a tracker are. Usually, after a target is initially detected, the radar is asked to do a number of different things. If it's a phased array radar, it can do them right away, because it can put in some, it doesn't have to scan around and wait 4 or 5 seconds or 10 seconds till the radar is at the same general area to detect the target again. A radar scheduler can send a blast out of targets to see, hey, was that a really target or false alarm? But what it's asked to do is continue to detect the target as it moves through the radar's coverage. And as I just mentioned, there are different ways you can do that with phased array radars and with track while scan radars, like an airport surveillance radar. And then what we want to do is associate the different detections with a specific target. Namely, ask the question, are all these detections from the same target? And we want to use range, angle, and Doppler measurements whenever they're available. We want to use these detections to develop a continually more accurate estimate of the target observables, position, velocity, etc. And of course, you know, velocity can just be measured by taking the position measurement twice, divided by the time between the two measurements, and you've got the velocity in that coordinate, either x or y or r or theta. And then also what you want to do is, after you have, you've collected a number of target observations that you're sure is a track, and it's different in early track than in later. You want to predict as accurately as you can where the target is going to be in the future, so that you can look right in that range azimuth space for a detection. So, because since most targets will be traveling at a constant velocity, or some may be accelerating, you have to take that into account. You want to look in the appropriate box when you do your association on the next scan. So the prediction of where the target is going to be in the future is an important calculation. And these are the functions of a tracker generally. There'll also be the function is when you don't get any more detections, to terminate the track, or to coast the track because the target you might be not have enough signal to noise ratio for one reason or another, and we'll get into that stuff later. But generally, these are the 4 functions of a tracker. Okay. Now let's look at the basis of continuous angle tracking. And let's look, first of all, here we have the target's real direction, and then we have bore sight of the antenna, which we call theta 0. And we have the antenna pointing. Its bore sight is over here with one beam A sub A, and its bore sight is over here somewhere with A sub B. And if we look at the amplitude for the illustration at the left, the two overlapping beams, we can see that the target is to the right of the antenna bore site, because A sub A is less than A sub B. You see here? Here's the target direction. And so where you get it smaller, where you get it bigger, you got to move in that direction. In the illustration here to the right, the target is pointing directly. The beams, both when the two beams you send out, beam A and beam B, give you exactly the same amplitude, the target is located at that bore site position. So what a lot of times we'll do is we'll have a target near its bore site, and we'll point a beam a little to the right, a little to the left, and if we get an equal amplitude, we know, hey, we're pointing, we know that the bore site of the antenna is in the target direction. Now we're going to look at amplitude monopulse in detail. Okay, amplitude monopulse comparison technique. That method uses pairs of slightly offset beams to determine the location of the target relative to the antenna bore site. So that offset we call the error signal. And this information is used to re-steer the antenna or the beam to keep the target very close to the antenna bore site. And we'll use a servo mechanism to go back and forth very close. For dish antennas, two offset receive beams are generally by using two feeds slightly displaced at the focus in opposite directions from the focus of a parabolic antenna. You'll see that in a minute visually. And the sum and the difference of the two squinted beams are used to generate an error signal. I'm going to show you in detail how that's done. Mathematically, there'll be a problem for you. The exercise is to derive the error signal. And each channel, there are going to have to be multiple receive channels. One for the sum, one for the azimuth difference, and one for the elevation difference. Each require a separate receiver. So to very accurately, using this amplitude monopulse technique to measure the exact position in the beam, you're going to end up having three different receivers. We call them channels, okay? Now, here we have the two overlapping antenna patterns. And if we take these two antenna patterns and we subtract them, we get a difference pattern. And this shows them in beam space. And if we get a sum pattern, we get a fatter beam. And here is what the error signal looks like. And these patterns, that is to say, the return that you get in the receiver from the sum pattern and from the difference pattern are complex quantities. They have amplitude and phase. And the error signal, which tells us where we are off bore site, is the magnitude of the difference divided by the magnitude of the sum times the cosine of the phase angle of the sum minus the phase angle of the difference. And this is what the error signal looks like for a typical single target that's within the beam width of the sum beam. Okay. It's just about linear when you're within the 3 dB beam width. It's very linear. Okay. Now, the question arises is, what we've got is, at the focal point of that parabola, we've got 4 horns. And they're receive horns. And we're looking at the front, and I'm going to denote them, A, B, C, and D. And there's a set of functions that we do to generate the azimuth difference, the elevation difference, and the sum, and then go into the receiver. Okay? Now, these symbols are for hybrid junctions, sums, and the antenna feeds. So we'll have an antenna feed for A, B, C, and D that will be connected down here. And to compute the elevation difference, which is here, we want to take B and let's see, B, we want to take A and B and we want to take them, and they will give us the delta pattern. And we want to take down here the C and D and add them together. And then what we get is the sum. And what we want to do is then take the sum of these quantities and combine them to get the difference in elevation and the difference in azimuth. Now, the way that's done, I'm going to show you algebraically in a minute, but the sum beam is made up of just adding together that block diagram I showed you on the previous view graph, just adds together the return you get from the electrode and you receive from all of the different 4 feeds. The elevation difference is B plus D minus A minus C. And that's the elevation difference, delta sub elevation. And the azimuth difference is A plus B minus C plus D. Now when you look up here, this was the location of the feed as you look at the feed, but notice the A plus C pattern, which is the upper one, is down. You're looking at the upper angles with the lower feed, is the point I want to make. Note that the lower feeds generate the upper beams. And here's what the beams look like individually from the 4 feeds. And you're adding them all up together to get the sum. You're subtracting the sum of these and the sum of these to get this, and likewise. Now, what you get out of the sum pattern in voltage is this, and the difference pattern, you get this. And when you take this quantity, the absolute magnitude of the delta of the difference minus the sum, in either elevation or azimuth, because you're going to deal with azimuth and elevation in parallel, different receivers. This is all going to go on in azimuth separately and elevation separately, times the cosine of the phase angle of the sum minus the phase angle of the difference. That comes out with this black dashed line, which is very linear, you can see. And so what you measure is when this error signal tells you how far off axis you are. And this is a whole beam width, which is quite good. And you can calibrate this very easily so that it's going to depend on your signal to noise ratio. And that factor of the error being proportional to the size of your cell divided by the square root of the signal-to-noise ratio. The more signal-to-noise ratio you get, the better your monopulse signal will be after you've taken out any bias errors. Now, this is how this is implemented. We have the transmitter and the duplexer, and it sends out the sum. And then what we have is coming back into the four horns, A, B, C, D, through a microwave combining network, which I'm going to show you in a moment. And that's going to output a sum, the delta azimuth and the delta elevation. And they will go into an azimuth receiver and a difference receiver, and an elevation difference receiver, and a sum receiver. And the sum receiver will be used for detection and range measurement, but then the sum receiver will also go in to the azimuth monopulse processor and the elevation monopulse processor, where you'll do coordinate transformation and then go to antenna drive servos, that if you're getting over near the target is getting over near the edge of the beam, it'll point, because the target is moved, it'll point the antenna back, keeping the bore side of the antenna as close to the real target location as possible. And these go to the antenna mechanical drives to keep the elevation and an azimuth right on target as best as it can. Now let's look at the microwave combining network. This is, I don't know, I was intrigued by this part. This is interesting because it's some neat things. How do you implement from the ABCD and microwave and come out with a sum, an elevation difference, an azimuth difference signal, and a one we don't use, just by using microwave components? Now, the first thing we do is we introduce a phase shift into the B level of 90 degrees and into the C horn of 90 degrees. And then we go into a device called, and there are three different kinds that are used, a hybrid junction. And what it does is it takes in A and B shifted 90 degrees, and it spits out, it sends out A minus B divided by the square root of 2 and J times A plus B divided by the square root of 2. And a hybrid junction over here where we've put the 90-degree phase shift in the C channel, we come out with differences. And then we cross over and we send through another set of four of hybrid junctions. And then what we see coming out are the difference pattern in elevation, and then a term not used, the sum pattern, and the difference pattern in azimuth. And this is with a 4-horn monopulse feed. So you can do it with 4 hybrid junctions. How do we implement that sort of thing? Well, here are the devices we use. Here is one that I have a picture of. It's called a Magic T. And these are all you'd send into each one of these, and I'll show you exactly which of the ABCDs. And we're going to talk later on in transmitters about waveguides and how we move energy around. And this is just a C-band Magic T. And a Magic T is one of these hybrid junctions. And this ridge that you see in the waveguide is in addition to the waveguide, that allows the waveguide to have much wider bandwidth than it ordinarily would if it was a purely rectangular waveguide. And I will be talking about that later. So this is what it looks like in 6 inches. We have another hybrid junction called a rat race, because here's port A, port B, port C, and port D. And just showing you in port A, we're going to look in detail how each of these worked. And then we have a 3 dB directional coupler, and the port A is here, port B is here, and then what these at these points where we have between the two waveguides that are connected, we have gaps. The energy is split off, and we have an output port C and D as outputs. Okay. Now let's just look, and I'm going to look in detail about how a hybrid junction of the magic T type works at C band. And you notice it's about a half a wavelength. If you look down, that's 1 inch, 2.5 centimeters. So, and 5.5 centimeters is a wavelength. So it's about a, wavelength over 2, a little less than a quarter wavelength, or about that in height. The signal input at port A, right here, divides in amplitude and phase between ports C and D, but does not appear at port B. Port B cannot support that propagation mode that it went in, this vertically, this mode. The signal input port into port B, that's the other input, divides equally but with opposite phases between ports D and C. It does not appear at port A, the same reason. If the inputs are applied simultaneously to ports A and B, their sum will appear in port C and their difference will appear in port D. And that's the function of one of those hybrid junctions. The same way with the rat race. And this takes a little more interesting, and probably I'll just go through this one. A signal in port A reaches the output port D by 2 separate paths. Port A goes around here 3/4 of a wavelength, and it goes through here, it splits here 3/4 of a wavelength. The two paths have the same path, lambda 3/4 of a wavelength, so they reinforce at port D. At input port B, it reaches port D through paths differing by a wavelength. Port B will go down to D, and it's a quarter wavelength. It will go all the way around to 5/4. The two paths will reinforce at port D because they're a wavelength apart. From paths A to D and B to D, they differ by a half a wavelength, and so you're going to get a different signal. And if the signals of the same phase are entered in A, the outputs at C and D are the sum in different channels. Neat. And lastly, a similar thing happens with a 3 dB directional coupler, which I'll just leave to you to look at, or you can read it in more detail in Skolnick. But those are the 3 main methods we use for hybrid junctions. Now, what happens after we get the sums and the differences? And I'll assume that what we've done is we're looking only at, say, the azimuth channel. You phase shift by 90 degrees the two signals with a mixer, and we send them in then into an A to D converter. We'll have the sum of the I channel and the sum of the Q channel. And here the I and the Q channel for the difference. And then we do A to D convert each one of them. And after the A to D converter, we just calculate the magnitude of the sum, the magnitude of the difference, the real part of the ratio of the sum and the difference, and the imaginary part of the sum, the real part of the difference divided by the sum, and the imaginary part of the difference divided by the sum. And that you just you can get the angles if you have the real and the imaginary part. You have the complex value, and if you have the complex value, you can just take the you can get the tangent of the overall phase directly from that, just by taking the inverse generating the tangent of the angle, and then taking the inverse tangent, and then you'll get the angle itself. Okay, so therefore we can get the error signal out in the computer for the azimuth, and there'd be an equal monopulse processor for the channel for elevation. Now, if you want to see how complicated in waveguides these guys can get, here are the input feeds to a S-band monopulse feed with an X-band central feed. It's very complicated. Okay? Now, this is the port from the S-band and the X-band transmitters, and they have to go through all these shenanigans to come out, and this is looking at the output, where we have the sum signals for the S-band, and here is the X-band feed at the center. So with this particular radar, you had located at the focus of the parabola in a Cassegrain mode a feed that measured in S-band the monopulse accuracy, and the X-band feed just measured the cross-section and amplitude and was kept on bore sight by the monopulse servo mechanism. Okay, and for monopulse processors, feed systems can get incredibly elaborate. And this is a photograph of a 12-horn monopulse feed to get even more accuracy. And this shows you the feed pattern where you would get the elevation angle difference and the sum and the azimuth difference out for this kind of a pattern to give you a better shaped, but much more complicated pattern. And here's a photograph of it. This was implemented by MIT Lincoln Laboratory for one of its instrumentation radars. Okay. Now let's look at angle glint, or angle noise. It's the fluctuations of the errors, as I mentioned before, that can be caused by a complex target I mentioned, like a twin-engine aircraft, multiple scattering centers. Anything with multiple scattering centers, it will glint and fluctuate. That's angle noise, we call it. And it causes a distortion of the echo wavefront, and it raises heck with the complex targets when it goes into a monopulse feed. A good example of this kind of glint is, you can imagine in a range azimuth cell, 15 birds flying in a flock that all have about the same cross-section. They're fluctuating somewhat, but they're moving back and forth. Now, over the time that you process, if you put into a monopulse processor multiple targets with multiple scattering centers, you get garbage out of the monopulse processor. For the bird case, because I've done that calculation, do I dare say 35 years ago? No, about 30 years ago. Anyway, glint can be a major source of error, is the bottom line. It can cause you to break track and when you're making angle measurements. And it's a problem at short ranges where the angular extent of the target is large, or you can have multiple targets within a given angle cell. And it's a problem for all tracking radars with closed loop angles, tracking, monopulse, chronicle scan, and sequential lobing, which is a technique that we'll get to. Now here's low angle tracking. I mentioned, we talked about that a little bit in fact, we went over it in great detail in propagation. But I want to remind you, and just go through this view graph quickly, that the target is illuminated via two paths, the direct and the reflected path. And the error in the measurement angle is caused by the glinting, the interference at low grazing angles, when, particularly like over the ocean where the radar coefficient is close to 1, or over flat land. And tracking targets at low elevation angles can produce significant errors if the elevation angle is low and can cause loss of track. And this is some kind called multipath signal, and the glint error due to this geometry, multipath error. This is data collected on an aircraft as tracked by an S-band phased array radar. Truth was supplied by a C-band FPS-16 radar. Okay? And this gives you the elevation error in degrees and the track time over minutes due to the low angle tracking error. And we see that the elevation angle in degrees is 3 to 1 degree, and the error increases significantly, and the azimuth stays pretty much the same, and the range is from 19 to 40 kilometers. But you can see as you go down in elevation angle, the monopulse error, the multipath error is significant. And the C-band radar has a significantly narrower beam width, so it wasn't bothered by the low angle multipath, which this wider, much wider beam would be giving multipath for. Okay, now we're going to take a break before we go on to the third section, where we're going to look at a different technique. That last technique we looked at was amplitude monopulse, and next we'll look at phase comparison monopulse and go through some of these other techniques in more detail.